So we'll go ahead and we'll record this for you too, so you guys can view this later if you'd like to. Anyway, so where we want to start today, we're kind of hitting back at the beginning of our 8-semester cycle here. So we want to start off with some conversions. So looking at a fraction to a decimal conversion. 7/16 means we have 16 pieces that make a whole object, and we have 7 of those pieces. So obviously we have less than a whole object. To figure out the decimal equivalent of that, we simply have to divide it out. We could do long division. Of course, 16 doesn't go into 7, so we have to add a decimal point. We bring that decimal point up, and we add zeros into it. 16 will go into 70 how many times? 4. 4 times 16 would be 64. Now, at this point, we ignore the decimal points once we've brought it up. We subtract. We have 6 left over. We add a 0, and we bring down another 0. Once we're after the decimal point, we can keep adding as many zeros as we want to get to where we need to go. Now, sometimes we'll be told that we need to round to the nearest hundredth or thousandth or whatever. This one, we're going to keep going and just see if it ends anytime soon. So 16 goes into 60 how many times? 3. 3 times 16 is 48. So we subtract, we've got 12. We add another 0 and bring it down. 16 into 120 is a little more difficult. I think we can actually get 7. Let's try 7. 7 times 6 is 42, so 2 carry the 4. 7 times 1 is 7, plus 4 is 11. So we subtract, we've got 8 left over. We'll add another 0 and bring it down. Now 16 goes into 80. Exactly 5 times. Now I showed you doing this the long way like this because there are going to be times on the job where calculator isn't in your pocket when you get there. Maybe you don't even have your cell phone with you. Or, I know for me at least, on construction sites, I had it happen all the time. The calculator would get flopped into the windshield of the truck. You get to the construction site, and the calculator was a warped blob of plastic at that point. So you have to be able to do some basic calculations by hand. With that said, I realize that at this point in life, you almost always do have a calculator on you. Your cell phone has a basic calculator at the very least. So something like this, rather than having to do it out by hand, you would just do, for 7/16, the numerator of 7 divided by the denominator of 16 to get 0.4375. If you have a whole number in front of your fraction, let's say we have 2 and 9/32. You can just simply ignore the whole number for now and do the 9/32. What am I going to divide here? What am I going to type this in? 9 divided by 32. Good. 0.28125. Then the whole number just goes in front of the decimal. So 2.28125. Any questions there? Not too bad. Going the other direction then, from a decimal to a fraction, requires us to remember, I hate going back to this with this group because it's a pretty basic concept, but we've got to make sure we're on the same page. Remember what those place values are. You know, this is the ones, tens, and hundreds going to the left of the decimal. Going to the right, it's the 1/10ths, the 100ths, 1,000ths, the 10,000ths, and on down. Well, if you look at those place values, they look a lot like fractions because that's what they are. Decimals are just a shortcut way of writing fractions that have those denominators that are powers of 10. So if I have 0.35, that's a shortcut for writing a fraction that has a numerator that is the numbers after the decimal, so that'd be the 35, over 100. Yes, the denominator is just the decimal place of the last digit, the hundredths. And then, of course, this can be done. There's going to be two things that can be asked of you here. You can be asked to convert to a fraction to the nearest unit, or you can be asked to convert to an exact fraction. If you're asked to convert to an exact fraction, that's exactly what you do, is you just reduce this. I heard somebody say you can divide them by 5. So we do that. 35 divided by 5 is 7, and 100 divided by 5 is 20. Perfect. Once again, if you have a whole number in front of it, let's do this. So let's go 5.0375. The whole number kind of gets ignored. That's going to be a whole number once you have a fraction as well. So all we have to work with is the part after the decimal point. The 375 is going to be over, careful, you got it, tenths, hundredths, thousandths, 10,000ths. I don't like shortcuts, but here's one that's a good one to use. There's 1, 2, 3, 4 decimal places. There has to be 4 zeros in that denominator when we start out. So now what can both of those be divided by? 5 will work. 25 would work also, yes. We can do 5. Let's do a 375 divided by 5 is what, 75. 10,000 divided by 5 is 2,000. And we can still divide both of those by 25 would work, yeah. We could have done 5 again if we wanted to, but 20, we see the 25, so just we'll use it. So 75 divided by 25 is 3. 2,000 divided by 25 is 80. So that reduces to 5 and 3/80. Any questions on those? So I said there's two types of converting decimals to fractions. This is if you're asked to convert to an exact fraction. That's the exact fraction, 5 and 3/80. The problem with that is if you're looking at a standard tool set, you don't have a 3/80 socket anywhere in your tool set or a 3/80 wrench of any sort. If you're looking at standard stock material, a lot of times it comes in usually to the nearest 64th. So a lot of times when you're doing a calculation, you need to convert it to a nearest certain unit so that you can find a standard stock item to use for it. So if we have 0.729 inches that we have calculated that we need for a piece, and we need to convert that because we only have steel stock that is to the nearest, I can't spell the day for some reason, to the nearest 64th of an inch. The process of turning that decimal into a fraction is totally different in this case. So we take the 0.729, and notice we left the decimal on there, whereas up here we took the decimal off and we put the place value of that last digit in the denominator. Here we leave the decimal on it and we just put it over 1. From here, we currently have a denominator of 1. We want a denominator of 64. If you remember your equivalent fractions, what do we do? What can we do to turn that 1 into a 64? Multiply by 64. Good. And of course, then we have to do the top, or the numerator, by 64. So we do 0.729 times 64. Gives us 46.656 64ths. So what that's telling us is we're between 46 and 47 64ths. Which one are we closest to? 47. So that's 47/64. So we might have 0.3298 inches, and we need to go to the nearest 32nd of an inch. Tell me what to do.
0.3298 times 32.
Perfect. We put the 0.3298 over 1, and then we multiply by 32. So 0.3298 times 32, 10.5536, which means we're going to be closest to which one? 11/32. Is that a process you guys have seen before? You guys okay with it? I don't want to spend a lot of time on these basic conversions because the last couple semesters have told us anything is that there's not enough time to get through everything. So we'll jump into the other stuff. So one of your big topics for this semester is belts and pulleys. If you're looking at the required belt length for a pulley system, well, a pulley is just a circle. If you have a 4-inch diameter pulley, the distance around that pulley is just simply the circumference of the circle. Who can tell me how to calculate the circumference of a circle? That's area of a circle. 2 pi r or pi times diameter, either one. Since most pulleys are rated in terms of diameter, we're going to use pi times diameter. So pi is just approximately 3.14 times the diameter of 4 inches. It gives 12.56 inches around that pulley. Now, belts don't go all the way around a pulley. Most belts wrap around a pulley like that. If the two pulleys are approximately the same size, the belt basically is in contact with half of the pulley. So the length of contact of the belt with the pulley is half of that circumference. So instead of pi or 3.14 times diameter, half of 3.14 is 1.57 times the diameter. Now, this is not a formula that I saw in your book, but when I did work with stuff, that was one thing that was important for us, was to figure out what size pulley you had to have in a system, because there's friction between the belt and the pulley, and you need a certain amount of force that needs to be able to handle, so you need a certain amount of surface area to get the appropriate amount of friction between your belt and pulley and a certain amount of tension and whatever. So that surface area helps you to figure out if you have enough contact between your belt and pulley, if you have enough tension on the pulley, on the belt, to get the force you need out of that system. But the next step, of course, is just the length of the belt between two pulleys. So what I'm going to do is we're going to label two pulleys here. The two diameters will be big D for the larger diameter and little d for the smaller diameter. And then we measure center of shaft to center of shaft from one pulley to the next, which we're going to label L. Actually, we'll label it C for this formula. Some of the formulas in your textbook call it L, some call it C. This one they use C for center to center. And so we're looking for the length of this belt approximately that wraps around the two pulleys. So there's really three main factors here. The first is the part that's in contact with the pulleys. This part here and this part over here. Well, that is approximately, if the pulleys are about the same size, that's approximately half of the distance around each of the pulleys. So one of the parts of your formulas is the portion of the belt that's in contact with the pulley. That's just the 1.57 times each diameter. So what they do is this. They add the two diameters, the big diameter and little diameter together, multiply by the 1.57. That is the combined distance that's in contact with the two pulleys. And then there's the amount of belt that goes between the pulleys. That's this portion here and here. Well, the length of each of those is approximately that center to center distance. So there's two of those. If your pulleys are really close to the same size, this is enough to calculate the length of the belt. But if they're not, well, two things happen. One is, this is at an angle. This would be your center to center distance. You can see that is a hypotenuse of a right triangle. It's a little bit longer than what just the regular center to center distance would be. So we have to account for that. The other thing that happens is if your belts or your pulleys are way different sizes, is this is not fully halfway around the pulley. And this one over here is actually more than halfway around the pulley because of those differences in diameters. So there's a factor that is in here to correct for that difference in diameter. To show you where this comes from, we'd have to get into trig. Trig is not a part of this semester. So this is one of the few times I'm going to throw a formula out there and tell you you're going to have to just believe me. So it's the difference between the big diameter and the little diameter squared, and then divided by 4 times that center to center distance. This calculation is basically a cosine calculation if you're into trig. So your total belt length is that length of belt between the 2C plus the length of belt in contact plus that correction factor. So let's look at an example here. So we have two pulleys, a 5-inch pulley and an 8-inch diameter pulley. The center of their shafts is 18 inches apart. So the calculation of our belt length is 2 times what goes in for C? 18, good. Plus 1.57 times what's going to go in our parentheses? 8 plus 5 or 5 plus 8, exactly right. Plus, then our correction factor, 8 minus 5, and then of course squared over 4 times 18. So when you enter this in the calculator, most of this can be entered exactly like it is. But one little change right at the end, you have to put parentheses around that. So when we enter this in, 2 times 18 is that first part, plus 1.57. Oops, thank you. Now, some of your calculators you can just put in the parentheses. Some of you have to put in times before the parentheses. I don't have to put it in on mine, but I'll put it in anyway. Times then 8 plus 5, close your parentheses, plus, so for your parentheses here, 8 minus 5, close the parentheses. If you have a scientific calculator, you'll have an x squared key there. Then divided by, and here's where you have to have that extra parentheses. So parentheses, 4 times the 18, and close the parentheses. It'll give you 56.535. So then depending on what you have for adjustments, that's either a 56.5 or a 57.8. Did you get to work?
Yeah.
Okay.
Yeah, I pretty much did that one.
Oh, yeah, it's not that bad.
That one wasn't too bad.
On your cell phone calculators, I think I showed you this last semester, but if you pull up your basic cell phone calculator and turn it sideways, it turns it into a scientific calculator. Okay. I'm going to have you guys try one, see just what you come up with. Give me a length of belt estimate for that system there. So our formula would be 4 times 20. 20 goes in for C, plus 1.57 times, then for your diameters, 12 plus 4, and plus the 12 minus 4 squared over the 4 times 20. So let's punch that in. Yes, 105.92. What you come up with? I see some confused looks. Did you guys get something different?
I forgot the square.
Ah, that'll do it. Oh, that should be 2. You're correct. Did I punch that in as 4 times 20? I did. So that would make it 65.92. Thank you. It's the first week. The little hamster is not totally on the wheel yet. Sorry about that. Good catch. So yeah, 65.92. Does that look better? Okay. Helps if the instructor doesn't screw it up on you, right? Okay, so we talked about proper belt tensioning. A common thing in engineering that comes into belt tensioning is doing a length over a certain factor. I worked in structural engineering where if you have floor trusses or floor joists, it was common to have an L over 240 or L over 120 deflection ratio. What that meant was the length of that floor joist you divided by 120, and that was how much it was allowed to deflect. So if it was a 10-foot floor joist, it was 120 inches long. Divided by 120, it could deflect by 1 inch before it was out of specs. If it was an L over 120. An L over 240 would mean it could deflect by half an inch or it would be out of specs. When we tighten a V-belt, they use a similar concept. And what they use, to simplify things, they just use the center-to-center distance. That's what they're using as their L. I realized that we just used L for belt length in the last example, and C was the center-to-center distance. So be careful to keep those straight. Your textbook uses L in this case for it. The way I've seen it done is actually they calculate the length of belt from point of contact of one pulley to point of contact of the next. But it's going to be approximately the same as the center-center distance anyway. And it's L over 64 is your allowed deflection if it is properly tensioned. So what that means is if you press at the center of that belt between the pulleys, the amount that it is allowed to deflect or move away from its natural path is that length divided by 64. So if that center-to-center distance is 16 inches, the amount that it's allowed to deflect is 16 over 64, or 0.25 or a quarter inch. So if it's 24 inches, find for me what is to the nearest 64th of an inch. What's your allowable deflection there? That's it? Okay, so you divide it out. Yeah, 24 over 64 is 0.375. Yeah, which is just 3/8 of an inch. You could have just done the 24 over 64 and reduced it as well. It would have reduced down to 3/8. There's a reason why I said to the nearest 64th of an inch. Because when you're dividing by 64, it automatically puts you to the nearest 64th. Then you just have to reduce it. Any questions on belt tensioning? So pulley ratios. There are all sorts of ratios that come into dealing with pulleys, and they all come back to the same main ratio. It is a ratio of diameters. And the pulley ratio itself is the diameter of the driven pulley over the diameter of a driving pulley. Well, which one is driven and which one is driving? Well, we're going to stretch my artwork a little bit here. Pretend that looks like a small electric motor connected to that pulley. If this one is 6 inches, this one's 14 inches, which one is the driving pulley? The 6. If we cut the belt, the 6-inch pulley keeps turning. It's the one that is connected to power. It is driving the other pulley. It's supplying the power to the belt. So this is the driving, and this is the driven. Your textbook actually simplifies this a little bit by using the notation. This is the driven pulley. They refer to this as the motor pulley. So that ratio becomes the diameter of the driven. Actually, they use capital D. I should be careful. the diameter of the driven over the diameter of the motor pulley. Doesn't necessarily have to be connected to the motor, but it is the pulley that is supplying the power to the belt. Like I said, the easiest way to think of it is if you cut the belt, that's the one that keeps turning. The driven pulley stops. So the ratio here, the driven would be the 14, the driving would be the 6, or the driving or the motor would be the 6. Now I realize you can turn that into a decimal by dividing it as 2.333 or 2 1/3. We don't want to do that. We want to leave it as a ratio of a comparison between two numbers. But we can reduce it by dividing both of those by 2 to get a 7:3 ratio. That is the pulley ratio. Like I said, that ratio describes a lot of things. It describes not just the ratio of diameters of the two pulleys, it's the ratio of the RPMs between the pulleys, it's the ratio of torque transfer between the pulleys, and all that. The biggest thing you guys need from your textbook is the ratio of the RPM transfers between the pulleys. Your textbook takes a typical way of throwing out a separate formula for every possible case. If you know one thing, then this is the formula. If you know these other things, this is the new formula. It's really just a case of linear motion transferred into rotational motion. We've already looked at the distance around a pulley. If this is the diameter, that distance is just 3.14 times the diameter. If we have a pulley that is turning, let's go with 400 RPM, and a diameter of 8 inches. The linear distance traveled by the belt on that pulley is the same as the linear distance traveled by any point on that pulley. Well, if it goes around once, that's just the circumference of the pulley, the distance around the pulley. If it goes around 400 times in a minute, that's just 400 times that distance around the pulley. So that linear distance is pi, or 3.14, times your diameter times your RPM. So for this pulley, that's 3.14 times 8 inches times 400 RPM. So we get 10,048. Now that is inches, and of course RPMs is revolutions per minute, so that's inches per minute. Typically though, distance and linear speed is not measured in inches per minute, it's measured in feet per minute. Exactly. We divide that by 12. It is 837.33 feet per minute. When we are looking at a pulley system connected by a belt, because of the connection of the belts between the pulleys, if I pick a point on the belt, the distance it travels around one pulley has to be the same distance it travels around the other pulley. So that means the bigger pulley is going to turn slower because it's further around. It has less RPMs to get the same distance. So if we look at it, the distance that's traveled around this pulley is 3.14 times the diameter times its RPM. The distance traveled around this pulley, I'm going to use little d because that's the smaller pulley there. The difference traveled around this pulley is 3.14 times its diameter times its RPM. Well, because the 3.14 of the pi is in both of them, we can divide that off, and it's just diameter times RPM is equal to diameter times RPM. Now, I don't have motors marked on here at all or not, so I'm just going to call this pulley 1 and pulley 2. So it's diameter 1 times its RPM. So diameter 1 times RPM 1 equals diameter 2 times RPM 2. So what that means is if I know the size of both pulleys and the RPM of one of the pulleys, I can find the speed or the RPM of the other one. So if I know this is 3 inches turning at 1200 RPM, connected to a pulley that's 7 inches. Again, it's size times RPM, so 3 inches times 1200 RPM has to equal 7 inches times whatever that RPM is. And now we're just solving an equation. So on the left side, we're going to combine those numbers. 3 times 1200 is 3600. On the right side, we need to get the RPMs by itself. To do that, we need to divide the 7. So 3600 divided by 7, what is that? 514.2857143 approximately. RPM. So what your book shows is something like this, that RPM 1 is equal to diameter 2 times RPM 2 over diameter 1. Well, that's exactly what we showed over here. That's exactly this formula. It's just they solved it for RPM 1. Every different piece that could possibly be missing, they have a different rearrangement of the formula. But this formula here fits every possible situation here. Let's say that we have a motor that has an 8-inch pulley on it, and that motor turns at 900 RPM. We have that hooked to some sort of a load, and that load has to operate at approximately as close as we can get to 500 RPM. So here now it's not the speed of the rotation we're looking for. We're looking for the size of the pulley that would be needed. So again, if we call this pulley 1 and pulley 2, really doesn't matter which is which. It's 8 times the 900, 7,200, has to equal whatever this size is. I'm just going to call it D times 500. And what do we do to solve that? We divide by the 500. What is that, 14.4 inches is what we get? We divide that out. So if your pulleys are incremented in ½ inches, you're probably going to use a 14.5 inch pulley. We could go back through the process if you want to figure out how close this is going to get to your 500 RPM. I mean, your 8 inches and 900 RPM isn't going to change. Now that we know that this is 14.5 inches or 14.5 inches, we can do the formula over again. 8 times 900 is going to be 14.5 times whatever that RPM is. And so it would just be 8 times 900 and then divide by the 14.5. So it's going to operate at 496.5 RPM. That's probably close enough to our 500, right? Any questions on that? We have similar situation for gears. That's my attempt to draw passable gear. I got an extra tooth in there. Let me. So pretend those look like gears. When we're dealing with gears, there's a concept called pitch that we'll talk about later. But pitch is the distance between teeth. And how pitch is calculated is it's just the number of teeth divided by something called a pitch diameter. And we'll talk about what a pitch diameter is later. But basically it comes down to teeth per inch. And we use the diameter rather than the circumference just because that's easier to calculate that way. But it really is a measure of how far apart the teeth are. For two gears to mesh together, they have to have exactly the same pitch. The teeth have to be exactly the same distance apart. So what that means is we can measure the size of the gear simply by counting the teeth. So the gear ratio is still the size of the driven gear over the size of the driving gear. Only we don't have to measure diameters to get those sizes anymore. We just count the teeth. So it's the teeth on the driven gear to the teeth on the driving gear, the motor gear. We use the M. So up here, again, pretend that looks like a little electric motor. Which one's going to go on top, the small gear or the large gear? Small gear. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 8 over 12, which of course can reduce to both divide by 4 to give us a 2 to 3 gear ratio. Just like with the pulleys, that gear ratio describes the ratio of RPM transfer, torque transfer, all of that between these gears. So let's say that the motor here is turning at 600 RPM. We can use a similar formula, but instead of diameter, it's going to be teeth times RPM. So for this one here, we have 8 teeth times an unknown RPM. Over here we have 12 teeth times 600 RPM. We can find that missing RPM. So we're going to multiply the 12 times 600 and then divide by 8. I'm going to do that all in my calculator just to save some time. So we're at 900 RPM. Again, your textbook kind of does a similar thing of for every missing piece in the gears, it gives you a different formula. But again, this formula covers it all. The number of teeth in gear 1 times the RPM of gear 1 has to equal the number of teeth in gear 2 times the RPM in gear 2. Does anybody has issues solving a formula like that? To me, it's way better, way easier than memorizing 4 different formulas depending on what piece you have missing. All right, it is 10:20. It's time for a break. So if you guys want to take 10 minutes, we'll start up again at 10:30. Okay, so I'm going to have you guys try one in your notes here. We have a variable speed motor with a 5-inch pulley on it attached to a machine with a 12-inch pulley that needs to operate at, let's go 750 RPM. Find what the RPM that motor should be set at to get as close as possible to that 750. So it's 5 times the RPM of the motor equals 12 times the 750 RPMs. So to solve that, we'll combine the 12 and the 750. So 12 times 750, then divided by the 5. 1800 RPM. Very good. I'm only going to put partial gears on here because I'm not going to get the number of teeth correct. So here we have a motor that has a gear on it with 12 teeth, and it runs at 500 RPM. It's attached to a device that needs to operate at 300 RPM. We need to figure out how many teeth it needs to have. Have you try that? We'll go over it in a couple minutes. So instead of diameter now, it's the number of teeth times the RPM. So 12 times 400 equals that number of teeth times 300. So yeah, 12 times 500 is 6,000. Divided by 300. 20 teeth. Any questions on those? So these problems get a little bit more complex if you have an intermediate pulley or gear in it. Gears aren't quite as bad. Pretend those are almost round. So let's say we have 3 gears here. Typically this intermediate gear is called an idler gear. All it is filling space and making the transfer between the powered gear and the loaded gear. And let's say that this initial one here is operating at 1200 RPM. So to find what our load RPM is over here, we have to go through both gears. So we start out with 45 times 1200 equals 15 times the RPM of that idler gear. So 45 times 1200 divided by 15 gives us 3600 RPM. And then we move on to the second interaction there between the idler gear and the loaded gear or the driven gear. 15 teeth times 3600 RPM equals 60 teeth times the RPM of that final gear. So 3600 times 15 and divide by 60. We get 900. As long as you have one where you know both, you can figure out all the rest, yes. Now you'll notice here, if we had just gone from the original gear, 45 teeth times 1200 RPM, to the final gear, 60 teeth times whatever RPM, 45 times 1200 divided by 60, we would have came up with the proper RPM. The reason is, this idler gear here is directly connected to both of the other gears. Where it makes a difference is again, we're going to stretch my artistic abilities incredibly here, where they're not directly connected to both gears. So let's say we have 28 teeth on this original gear. Let's go 600 RPM. Let's put this one here at 18 teeth. This one over here at 21 teeth. And this final destination here, let's go 42 teeth. So what's going on here is these two gears here in the middle don't connect to both of the other gears. They're connected to each other by a shaft. And that changes things. So what we have to do is we have to find the RPM of this gear. So we'll start out with the 28 teeth at 600 RPM. So 28 times 600 equals 18 teeth times that RPM. So 28 times 600 divided by 18 gives us 933.33 RPM. And that tells us that the 21 tooth gear, because the 18 tooth and the 21 tooth are connected on a shaft, they have to be turning the same RPM. So that one is also 933.33 RPM. So we start off to find this final RPM of the 21 teeth times the 933.33. Now notice I didn't clear my calculator because that is a weird continuing decimal. It's actually 1/3. I left it in my calculator, so I'm going to keep going with that calculation when we redo this. Equals 42 teeth times our final RPM. Something like that. Yeah. So we keep the 933.333 times 21. And then we'll divide by 42. So, oops. Let's try that again. Let's get the 2 in there. There we go. giving us 466.66 RPM for that final gear. So in that case, we can't just directly go from the first gear to the last gear like we could up here. We could have skipped the idler gear in this one. And the only reason we could skip it is because that gear contacted both of the driven and the driving gears. Here, because there's a shaft in the middle, we have to go through every interaction to get to that final amount. The same is true for belts. This is a little bit simpler because it's easier to draw. So let's say we got a 6-inch belt here on a motor that is turning 800 RPM. Connected to a 20-inch pulley that has a 5-inch pulley connected to it, going to a final that is a 10-inch pulley. So we need to find the RPM here. So it's the same type of thing. We have to go through both interactions because the 20-inch and the 5-inch pulleys, technically they're connected on a shaft. Even if they're welded to the side of each other, they're sharing a shaft. So we have to go through the double calculation here. So we start out, tell me what to start out with here. 6 times 800 equals? So 20 times whatever that RPM is, yep. So yeah, 6 times 800 divided by 20. Perfect. So 240 is the intermediate RPM here. And because they are connected that way, both the 20-inch and the 5-inch turn at 240 RPMs. So now, what do we do to get to the RPM for the 10-inch? 5 times 240 divided by 10. Good. So we get 120. You got it. You'll notice there, by the way, the ratio of the pulleys, 5 to 10, is a 2 to 1 or 1 to 2 ratio. Ratio of the RPMs, 240 to 120 is a 2 to 1 or 1 to 2 ratio. The difference is it's reversed. The bigger pulley has the smaller RPM. Well, when we're dealing with pulleys and gears, an important concept is torque. Torque is a force that causes a rotational motion. So when we're dealing with torque, we have to start off with a center of rotation. For a pulley, that would be the center of the shaft that the pulley is on. And then we have, depending on the textbook, they call it a torque arm or a moment arm. I'm used to calling it a moment arm. I believe your textbook calls it a torque arm or whatever, but same thing. So and then of course there is an applied force. So the torque is equal to the applied force times the length of that arm. So if I have a 4-inch arm, actually I should be careful. Let's do a 4-foot arm first with a 20-pound force. My torque is 20 pounds times 4 feet. 20 times 4 is 80. Feet times pounds, or pound times feet is either foot pounds or pound feet. I believe your textbook uses pound feet as the unit instead of foot pounds. They're exactly the same unit. You'll hear me say foot pounds just because that's the unit I'm used to using. That's your technicians use? Foot pounds, yeah. Or inch pounds. But yeah, we're not getting into Newton meters. Actually, it gets into the argument of, metric system versus standard. A lot of your companies that do international business now are switching over to the metric system. IBM did it 6 or 7 years ago. They figured in the first year alone, it saved them over $6 million, not having to take the time to dimension everything in metric and standard, because some of their parts were produced overseas in the metric system, some were produced in the US with the standard system. Well, you've got to convert all those measurements. And then the mistakes that are made in those conversions, or the rounding in those conversions, the fact that the parts wouldn't quite fit together in precision parts, it was a significant savings. And there are a lot of other international companies that are going to that. So the metric system is actually easier once you get used to it. It's just saying Newton meters is just kind of weird for me when I'm so used to foot pounds.
It's working with a lot of foreign machines. It's really weird. Like, like we do injection molding, so you
Mhm.
do like mold platens and stuff. The platens where the mold actually bolts in. It's like, we'll give you dimensions, all metric, but then it's just some goofy standard number.
Yeah.
And that's how we order it,
Oh, sure. Yeah, so it's given as like 48.2 millimeters, and it's actually like 3 inches. Yeah. Yeah. Yep. When I was in middle school, and I'm going to date myself a bit here, like 35 years ago, when I was in middle school, my middle school science teacher was preaching, within 10 years, we're going to be switched over to the metric system. And you guys probably heard the same thing maybe 5-10 years ago. Yeah, they're probably still saying the same thing in middle school. It's going to happen. It's just we've really resisted it. What the U.S. government has done is, rather than making a full government change, they've allowed every regulatory agency to do it on their own. Like, you cannot buy a pound of gunpowder or a liter of whiskey. Anything regulated by the ATF, alcohol, tobacco, and firearms, has to be bought and sold in metric units. So the main units are metric. I think the FDA is probably the next one that's scheduled to shift over. But you see all your nutritional information is in grams and milligrams already. They're going to just take it all, get rid of the whole fluid ounces and just go to milliliters and stuff at some point.
So one thing that never made sense to me, so we have a couple old tool room guys, right? And
Yep.
Old machinists, and they say that standard is more precise than metric. And I never understood that. They always get mad whenever I have them make something. It's like I give them measurements and metrics. It's just easier. They won't do it.
Standard is only more precise if you start in standard units, because then you have the round off error when you convert to metric. Otherwise, metric is way more precise. It's way easier to get to a small precise unit.
It's way easier too. Trying to switch wrenches between a standard wrench. I mean, you're trying to convert fractions in your head to figure out what wrench is your next one down, but millimeters. Oh yeah, I just gotta go down.
One number, yeah.
Yeah.
Well, and 100th of a millimeter is still a smaller unit than 1,000th of an inch. So it's way more precise when you get into that. Yeah. I mean, you talk to the old timers and they will, standard is way better. It's just because they're so used to it. And they can be more precise in it because they just don't know what to do with the metric. I'm telling you, everybody in the world but me is wrong. No, just kidding. I'm not quite that bad. So if we have a 90-pound force on an 8-inch moment arm, we have a force of 90 pounds times, why did I write in 8/12? 12 inches in a foot. So I have to convert that into feet. The easiest way to do that is just to turn it into a fraction over 12. So that's 90 times 8 divided by 12 is 60 pound-feet or foot-pounds. So if I'm looking at a 4-inch diameter pulley, and it doesn't matter what the size of the pulley it's connected to is, if it has to be able to pull with a force of 200 pounds, what torque does that motor have to be capable of producing that's turning that pulley? Well, it's the force of 200 pounds times that moment arm. What's the moment arm going to be? Careful. Why is it 2 over 12? Because the diameter is 4, the moment arm is just the radius. So it's half the diameter. So 200 times 2 divided by 12 gives us 33.33. So preferably you'd have at least 35 foot-pounds of torque available from that motor. Well, how do we know what a motor is capable of supplying? It is not exact, but a good approximation of the torque developed by a motor it's a constant that comes into play. This comes from the fact of horsepower being, 746 foot-pounds, or I can't remember the exact number anymore. No, 746 watts is electrical horsepower. I blanked out on the conversion between foot-pounds and horsepower. But the constant 5,252 comes from that conversion of the amount of foot-pounds in a horsepower times your horsepower. And then for most motors, it depends on the RPM they are running. So if you have a 2.5 horsepower motor at 1,300 RPM, the developed torque, 5,252 times the 2.5. I'm just going to put it in as 2.5 over 1,300. So 5,252 times 2.5 divided by 1,300 should be 10.1 pound-feet of torque. So if we have a 4 horsepower motor operating at 400 RPM, find the torque that that motor has developed. Yep, so we got the 52 times 4, or times 4 over 400. Yeah, 52.52. Pound-feet. Not so bad? Let's look at it from the other side. We have a 1 3/4 horsepower motor that needs to generate 9.1 pound-feet of torque. What RPM should it be operating at? So we need 9.1 pound-feet or foot-pounds of torque equals 5,252 times 1 3/4. We're just going to put it as 1.75 over RPM. I use this example because what we're solving for is on the bottom of a fraction. That makes this a lot more difficult to do. When you're asked to solve for a number that's on the bottom of a fraction, the easiest way to do it is to make it into a proportion. So we put the 9.1 over 1, and then we will multiply out this part here, the 5,252 times 1.75, gives us 9,191. And to solve a proportion, if you recall, the process is cross, multiply, and divide. So the 9,191 times 1, which is just 9,191, then divided by the 9.1. What's that? Perfect. 1,010 is our RPM. You got it. So that motor needs to be operating at 1,010 RPM to achieve 9.1 pound-feet of torque. Let's have you guys try an example of that. So find the required RPM. If we have 3.5 horsepower motor that needs to develop, let's just go 27 pound-feet of torque. So we put the 27 over 1, then we'll start with this part here, the 5252 times 3.5, gives us the 18,382. We do that times the 1, which doesn't change anything, divide by the 27. 680.81 approximately, yep. RPM. Any questions on that? Let's go to the next step. So we're going to find the required horsepower needed to supply 30 pound-feet of torque at 2,600 RPM. So we have the torque, the 30. 52 is our constant still. We're looking for the horsepower at 2,600. So now here, we can just solve an equation. So we got the 30 here. On the other side, we have to get horsepower by itself. It's being divided by the 2,600. So to get rid of the 2,600, we do the opposite. We multiply by 2,600. So 3 times 2,600 is, or 30 times 2,600 is 78,000, I believe. Equals the 5252 times the horsepower. We got rid of the 2,600. Now we just have to get rid of the 5252 by doing what? Yeah, it multiplies the horsepower, so we divide. So 78,000 divided by 5252, giving us 14.85 horsepower. So probably a minimum of a 15-horse motor. That's getting up there for an electric motor, yeah. It took me a while to get my mind around higher RPMs meant low torque, because higher RPMs means more power. Most motors generate more power at higher RPM, but less torque. And so that took me a while to get used to that idea. So we're going to find the horsepower for a motor turning an 8-inch diameter winch at 13 RPM to lift an 1,800-pound load. This is actually pretty much the same as the last problem, only I'm asking you to do an extra step. The first step is to find the torque needed. And so the torque needed comes from the 8-inch diameter and the 1,800-pound load. So it's that load of 1,800 pounds times, not 8, but 4 over 12. Because again, we have to convert the inches into feet. So 1,800 times 4 divided by 12 gives us 600 pound-feet of torque. So then we move to the next step, finding the horsepower. We know we need 600 pound-feet of torque. I'm just going to leave the units off to make it easier. Equals 5,252 times our horsepower over 13 RPM. Perfect. So we start with the 600 times 13, and then divide by the 5,252. So 1.485 horsepower. What do you think? Good stuff? Yeah. That electrical stuff had a lot of formulas, that's for sure. And the fact that you derive the horsepower from so many different things. There's, 8 different formulas for power from. One last thing I promised to talk about. We're not going to get to friction today, but that's okay. We'll just throw those 2 questions off the worksheet. Pitch of a gear. So gear pitch, it's actually what we call diametric pitch. Is calculated, as we said, the diametric pitch is equal to the number of teeth divided by, so dP is diametric pitch, both capital letters. D with the little p is the diameter, that's the pitch diameter. And what the pitch diameter is it's a working diameter of the gear. And we're going to try to draw a picture here, but bear with me. So pretend those look like teeth on a gear. And we're just going to stop there. There's an inner diameter of the gear, which is just the hub inside the teeth. And then there's an outer diameter, which goes to the outside of the teeth. Well, the pitch diameter is somewhere in between there. When this gear meshes with another gear, there's a certain amount of clearance. Why do my teeth on my gears always look like they're from Rusk County? Sorry. No offense to anybody from Rusk County. But everybody around here picks on Rusk County. It's our Appalachia of the northern Wisconsin. Yeah. Sure. So anyway, there's some clearance here where that gear doesn't go all the way into the tooth doesn't go all the way into the central diameter of the other gear. So there's some clearance there. But what there is it's a working diameter where if I have that circle on one gear that's that distance out among the teeth. And the circle on the other gear that's the same portion of the way out of the teeth, those two circles are what we call adjacent. They just touch. The diameter of that circle is the pitch diameter. Well, you'd have to get into spur gears, and there's a whole ton of formulas for spur gears that you can calculate from the depth of the tooth or the working depth of the tooth, the clearance of the teeth. All of those things can be used to find that pitch diameter. We're not going to get into that here because that would be a 40-minute lecture all on its own. But just know that is the diameter they are talking about, is that diameter of that circle that is the two circles that touch. They're part way out of the tooth from the center of the hub. So if we have a gear that has a pitch diameter of 4 inches and has 28 teeth, the pitch, the diametric pitch, is 28 divided by 4, or 7 teeth per inch of diameter, is what that rate is. And like we said before, in order for two gears to mesh, they have to have exactly the same pitch. With that, I need to make sure I give you plenty of work time, so we've got 15 minutes left here.